So now we are going to talk about the irrationality of a certain type of number, which is the square root of any integer that is not a perfect square. So in this case, it is a square root of 2, and we want to prove that square root of 2 is irrational. That means square root of 2, this number, cannot be written as a ratio of two integers p and q. So one thing to remember as a general principle here is that square root of an integer is either an integer or an irrational number. It cannot just be a rational number. If it is a rational number, then it has to be an integer. So we have to prove that square root of 2 is irrational. That means, what that means, that is, prove that square root of 2 is not equal to p divided by q for any integers p and q. Of course, we assume that q is not equal to 0, of course. But so the way this proof goes is a proof what we call as a proof by contradiction, because we cannot test all possible integers p and q. There are infinitely many of them. So we have to come up with a general methodology or a general reason that rules out all integers p and q, rather than listing out integers one by one, which is impossible. So we assume the proof goes as follows. So you assume that square root of 2 is equal to p divided by q if possible, and then we reach a contradiction. So this is called a proof by contradiction, which shows that square root of 2 is not writable as p divided by q. So let's say, suppose, if possible, let's say square root of 2 is equal to p divided by q for integers p and q. Now clearly p and q have to be where q cannot be equal to 1. P and q are going to be co-prime, because square root of 2 has to lie between square root of 1 and square root of 4, which is 2. So we know that 1 is less than square root of 2 is less than 2. So p and q are well, q cannot be 1, because that would mean that square root of 2 is an integer, which we know is not. So we can take them to be with no common factors, or we can assume that p and q are if there are common factors between those numbers, then those are all removed. So p and q are co-prime. So let's rearrange this equation now. So square root of 2 is equal to p divided by q. So that means that p is equal to q times square root of 2. So let's square both sides, which means p square is equal to 2q square. Note that p and q are both integers, and they don't have any common factor as assumed. What this means is that, so this p is an even number. So this is an even number. It is 2 times something, so it is an even number. So p square is an even number. That must mean that p is an even number. P is an even number. And therefore it also means that, so this 2q square is an even number, we know that, and it is a perfect square because it is a square of p. So so p is an even number. So p square is actually, let's say p is equal to 2m. So p square is 4m square. That is, it is divisible by 4, because square of an even number will be divisible by 4. So 2q square is divisible by 4. So therefore it must mean by q square is divisible by 2, because you take 1 2 out. But if q square is divisible by 2, that means it is an even number. Then that must mean that q is an even number. So we have reached a conclusion that p is an even number and q is an even number. But we started with the assumption that P and Q are co-prime numbers. They don't have any common factors. But here we exhibited a common factor, which is 2, because they are both even numbers. So this is a contradiction. And therefore there is no way to write square root of 2 as P divided by Q, which proves that square root of 2 is irrational. So a couple of remarks here. So this method can be extended to more numbers here. You can prove similarly square root of 3 or square root of 5 or square root of any prime number can be easily obtained through this method. We can show that it is irrational. Moreover, you can show that square root of any integer that is not a perfect square is also irrational. The same method can be made to work there. So that was one remark. And second is this just goes to show the general methodology in these types of arguments, that when we want to show that something is impossible, like square root of 2 cannot be written as P divided by Q, then the proof usually goes by as what we call the proof by contradiction. That assume that something is true, assume that square root of 2 is equal to a ratio of integers, and then reach a contradiction. This is a somewhat different flavor of proof rather than, let's say, proofs in geometry, where we prove that let's say equilateral triangle has all sides and all angles equal. All sides are equal, therefore all angles equal. Those proofs don't go by proof by contradiction. Those are just straight direct proofs from the axioms. But this is a different flavor of a proof, so that's why I thought this might be interesting.